Hi there, thanks. I'm happy to be here to describe some of the new and exciting results from Juno. We have quite a few people on board. I'm going to give you kind of an overview, we're going to show you some stuff about the Great Red Spot. We went over that last July, and we saw for the first time what it looked like really up close and personal, and what it looked like underneath the cloud tops. And so Andy Ingersoll here, my colleague and Juno co-investigator from Caltech, will go in and show you some of the data from that. Heidi Becker from JPL will show you some of the new radiation data that we're getting. Juno, of course, goes very close to Jupiter and is very susceptible and to the very harsh radiation environment. And we've learned some things about the environment and the regions and discovered some new components to that radiation. She'll give you discuss that. And then Candice Hansen from Planetary Science Institute is the lead for our Juno Cam instrument, and that's an instrument that takes all the pictures, the beautiful pictures of Jupiter, and we put them on our website and for the public to digest. In fact, they get to process the images. In fact, all the images we'll show you today are actually made by citizen scientists or the public, and she'll go through that outreach program, which was sort of a big experiment where we just took all the data and put it right on the website, and the public's really responded. And you'll see a lot of both science and art. They're expressing themselves. So I want to start off with an animation. We're going to take you on a little bit of a journey. So we've seen some incredible pictures of Jupiter close up. It's really a piece of art. We're going to take you on a journey like you're on the spacecraft. We've made an animation taking some of the photos and actually going to fly you very close to Jupiter and show you what it would be like if you were seated on the Juno spacecraft. And we'll go a little bit further, and not only will you see the view from Juno, but we're going to take you in, and because we have some instruments that can see down deep, and we can measure the temperatures and some of the structure down there, which I'll talk about later. But we're going to take you for a ride down into Jupiter, a few hundred kilometers down, and come out the Great Red Spot. So I'll start that animation if I can figure out how to do that. That one wasn't it. So here you're starting. You'll see an altitude chart. So we're above the atmosphere here, flying in. And you'll see that we're going over these incredible white clouds that were discovered by Juno. We had never known really those white ammonia clouds existed at that level. Now we're going to go right into one of these dark holes. And you're in, and you'll see the temperature rising very quickly because the temperature goes way up as you go into Jupiter. And then you're turning in, and now you're in the Great Red Spot, and we're going to poke out. And you'll see that you're right above the Great Red Spot. And you see it also as full of dynamics and cyclones. And we're seeing very high resolution data because Juno's really close when we're taking these images. So that gives you a little bit of a ride on what it would be like if you were to be able to go to Jupiter and go in. Of course, down below those cloud tops where the sunlight gets blocked, it gets pretty dark, but it's pretty warm down there. And there are some lightning in different places. Okay, so now I'm going to turn over to Andy, who will show you some of the data more specifically from the Great Red Spot and talk about the science.
Well, what's so special about the Great Red Spot? It's a 150-year-old storm. And anyone who reads the papers or and looks at the weather map or tries to decide what's going to happen in the future knows that a weather forecast doesn't exist beyond about a week, which is because our storms don't last that long. They're constantly getting broken up, and so you can't forecast something that isn't going to be there next week. The red spot, 150 years at least. It may date back to the invention of the telescope, but it's not clear that people were watching throughout that period, but certainly into the 19th century. And It's larger than Earth, so it's a giant storm. The winds flow around it 3 times faster than the Earth's jet streams, by which I'm referring to the winds that make a trip from Los Angeles to New York shorter than back the other way. And why are we as scientists interested in the red spot? We want to understand how weather works. We'd like to understand why we can't forecast the weather more than a week ahead. And seeing weather and seeing very different kinds of weather in different contexts helps us understand. And that's really how we make progress in this business. We build better weather models if we've tested them, really stress tested them on systems that are extraterrestrial in this case. Let me see if I can do this. Try it again. These are 3 pictures taken by the Juno spacecraft with the Juno cam instrument, which is a very wide-angle instrument. Looks like this. So you get a lot of distortion, almost it sees from horizon to horizon. And so you get a lot of optical distortion like a amusement park mirror. But you can see this feature as Juno's passed overhead. Juno passes overhead, really skimming the tops of the clouds every, 53 days. And it just so happens one of those passes back in July passed over the red spot. It's the only pass we've had so far, but we hope to get more. It's not all visible light, although that's what you're seeing here. Juno is looking in radio waves, microwaves, and can measure the temperatures from levels that are hundreds of kilometers, let's say 300 kilometers below these visible clouds. And so it gives us our first look at the roots of the red spot, because part of understanding this 150-year-old feature involves the roots, which we really don't know about. Now, let me show you the highest resolution view of the red spot. I love this picture. My favorite feature inside here is that little group of very small clouds up at about 1 o'clock relative to the central red eye of the red spot, which we really didn't expect and really don't quite understand. We see lightning on Jupiter, but we don't see lightning under the red spot. The winds around the red spot are counterclockwise, which means it's an anticyclone. But why it doesn't have lightning storms, still a mystery. Mysteries are good. If you knew all the answers before you got there, you wouldn't be learning anything, and we're learning a lot. So I want to tell you about Juno's probing beneath these clouds and finding the roots of the red spot, and hopefully that's part of the roots of our understanding. I'd like to also show you this structure in motion. It's a cheat. I've cheated. I want to give you a 10-hour view of the red spot as if there was no day and night. So you're up there with a sun-like beam shining down in the red spot, and so you can see it even though it's actually dark because you've got your fancy eyes. So this is what the red spot's doing. it resets every 10 hours of simulated time. And as I say, these winds are 3 times faster than the Earth's jet streams, 3 times hurricane force. This is not just a curiosity, but it helps us with the roots, because anticyclone is a high-pressure area, and you create a high-pressure area if there's warm air below, because it causes the air above to expand. And the amount of warmth below is connected to the speed of those winds. And that's what the microwave radiometer is doing, is measuring temperature very deep down. So here's what the microwave radiometer has shown. It has 6 wavelength channels, and channel just means wavelength, and they sample different levels in the atmosphere, and this stack of strips shows what each one is seeing. White color is warmer than its surroundings. Red color is colder than the surroundings. The very top panel is a visible light image made by Juno and the other 6 below it are the infrared. And there's a scale on the right that shows you the depth from the cloud tops. And you can see that the deepest channel, it's numbered channel 1, is seeing 350 kilometers down with broad averaging, but it's white in this color scheme, which means it's definitely warmer than its surroundings at that great depth. And so the root of the red spot goes down at least to 350 kilometers. That is the new result. How deep it goes beyond that is still TBD. Juno has other ways of measuring a much deeper root if it exists, and that's using the gravity signal as it passes over the red spot or any other feature, because you don't have winds without having a shifting of masses, and of course gravity is the effect of masses. So we hope to get deeper handles on the roots. I'll just say that the amount of warmth that you see in this microwave image is consistent with the winds that we measure at the tops, but we won't know fully how deep the winds go until and Scott, maybe you know when our next red spot pass is, but we've got one coming up. Thank you.
Hi, good afternoon. I'm very happy to be here to talk to you about the radiation at Jupiter, because in our first year at orbit around the planet, we've learned a lot of things about it that we didn't know before we went. And Juno flies so differently than any other spacecraft has flown before around Jupiter that's allowed us to see things, to detect things that nobody else has ever seen. And today we'd like to talk about 2 of those discoveries with you. This is an artist's rendition of the high-energy electron radiation belts very close to the planet. And Juno's trajectory threads the needle between those radiation belts and the cloud tops. We get closer than any other spacecraft has ever gotten to Jupiter. We're about 2,100 miles from the cloud tops at our closest approach during every science pass. And other spacecraft have gone into the inner radiation belts, but never quite as far as we do. In 1974, Pioneer 11 got as close as 27,000 miles from the cloud tops, so a little more than 10 times further away than Juno does. And in 1995, the Galileo probe took a single path very close to the equator into the atmosphere of the planet at a single longitude. So Juno is the first spacecraft that has ever sampled the inner edge of the radiation belts at high latitudes. And that's allowed us to see two very interesting things. And the first is a new population that we didn't realize was there before we went, and it's right on the equator, just a little bit above the atmosphere. And these are not high-energy electrons like most everything else that's in the region where we fly. These are high-energy ions. They're hydrogen, oxygen, and sulfur. They're discussed in Juno's special edition of the Geophysical Research Letters in an article by Coleman et al., and they were discovered by Juno's JEDI instrument. And the theory that's discussed in that paper is that where these particles were actually born is out around the moons of Io and Europa in gas clouds. And as those particles come in as neutral atoms that are very energetic, some of them eventually hit the atmosphere. And when they do that, electrons get stripped away, turning them into high-energy ions. And they've gathered in this region near the equator. This is something that the Galileo probe never saw, and they actually couldn't have seen it because they were looking for even higher energy ions. So this is a gap between the clouds and the radiation belt that actually isn't a gap after all. And only Juno was able to see it because of where we fly and the instruments that we have on board. Second population that we've seen is in a different location in Juno's trajectory. It's in the high latitudes. And we see these as our spacecraft grazes the inner edge of the radiation belts every single science pass. So as we go through regions that are filled with relativistic electrons, we hit a second population that isn't electrons after all. It's actually very high energy ions, even higher than the ones at the equator, which themselves are moving at nearly the speed of light. The ones in the higher latitudes are hundreds of times more energetic even than the ones at the equator. And the kind of special thing about this particular discovery is that the only way we were able to do that was by using an engineering instrument on Juno as a science instrument. And this next animation helps to explain exactly how that works. This is our spacecraft star tracker, which is actually the most heavily shielded thing on Juno. It's more than 6 times more heavily shielded than our radiation vault that you may have heard about. But even with all that shielding, this navigation camera is still susceptible to penetrating radiation. Very high energy particles, relativistic electrons and ions, can still, some of them get through that shielding, and when they do, once they hit the detector inside, it creates these white dots and squiggles and streaks that you see in this simulation. That's happening because energy is being released by those particles. And we knew that we would see that in the high latitudes. We were prepared for that. We designed Juno for that. What we didn't expect was that in between all the electrons, we would see something else that was different. This is an image that was collected in December, on December 11th, during our second full science pass. And in between all those white dots, which are the electron noise, we saw something else, a handful of signatures that were hundreds of times brighter than anything an electron could possibly make, more than 10 times brighter than anything you would expect a proton to make. And that's showing us that we have a signature of something that's a heavier ion, something more highly ionizing that will dump more energy in the detector. And those are those spikes that you see when we tilt the image. We don't know exactly what type of ion they are yet. The species and where they might have come from is something that we're still studying. But this is a new population that we didn't realize would be there. So with that, I'll leave you with our composite new view of what the inner radiation belts look like, the very high energy electrons that are shown in the orange, and the new high energy ions that we now see at the equator and in the high latitudes. And with that, I'll hand it over to Candy.
Thank you, Heidi. A year ago, at the Juno press conference, I described a citizen science experiment, an outreach experiment that we were about to embark on. We had decided to try to give the public an opportunity to participate on an instrument team on a flight mission in a realistic way, to be members of a virtual imaging team. And a year ago, I wasn't sure this was going to work, but we were willing to give it a try. Today, I'm happy to describe the success of that experiment. In order to make this happen, we put together a website. This is the JunoCam section of the Mission Juno website. And the page is devoted to JunoCam. And there are 4 ways that the public can become involved and participate and actually be essential members of the team. We don't have people waiting in the wings in case no one shows up. We really put it all out there and took this leap of faith. So in the planning section, we have asked amateur astronomers to send their telescope images of Jupiter for us to use for planning purposes. We have had over 3,000 contributions to date. In the discussion section, we invite people to weigh in on what we think we should take pictures of. And so we've asked the public to identify a point of interest, tell us why you think it's interesting, give it a name, and tell us, and then that becomes a target. In the voting section, that's where you make the tough decisions. We only have so many resources. We have to worry about the camera and getting too warm and so on and so forth. So we have to make intelligent choices. And so we invited the public to help us make those decisions. And the 4th section, the image processing section, is where we post raw and lightly processed images and invite the public to download our images, our JunoCam images, and upload their contributions, their own creations. And I'm going to focus mostly on that section. I'll add that we're in the process of building another page that's going to be science analysis, where we do participatory science analysis as well. We've had, to the Mission Juno pages, we've had over 1 million visitors, and page views almost 6 million, which is important because that shows that people didn't just come and take a look, they drilled down and got engaged. This is an example of a contribution from our citizen scientists. I am going to be showing the credits on each and every one of these. This particular image was processed first by Gerald Eichstadt and then by Sean Doran. And basically, what Gerald figured out how to do, and this is not easy, is he figured out how to take out the brightness gradient from the terminator, from the shadow, the night side, to the bright limb. And so there's a natural brightening as you go from the shadow to the subsolar point. He figured out how to take that out. And that forms then the basis for many other contributors. They take his image then and they do different color processing and different, all sorts of different things with the data. You heard about the Great Red Spot scientifically. This is what the Great Red Spot looks like to an artist. And this was, I think, for me, one of the most heartwarming aspects of this has been the contributions that we've gotten from the artistic community, from people who relate to our data much differently than we do as scientists. You never know where this stuff's going to show up. The top panel is from our 8th close flyby, and Gerald and Sean basically put together that strip of images. On the far left is the image of the north polar region of Jupiter, and then on the far right is the south polar region. The time that elapsed between those two images is about 2 hours, And you can see how close we get to Jupiter and then we recede away again. So that's a 2-hour perijove pass. Sean tweeted that out, and the next thing you knew, it was turned into a wall hanging and posted in a facility somewhere in Lund, Sweden. So this stuff travels. We put on an art show at the Division of Planetary Sciences meeting in Provo, Utah, just a couple months ago. And again, showcasing some of the more artistic contributions, and we hope to do more of this in the future. This is another Gerald and Sean contribution. I'm honestly quite partial to their color scheme. These are stretched colors. They allow us to see things that are actually in the original data, but that don't really come out so easily to our eyes. When you stretch the color a bit, you start to see a lot more detail in the clouds. And my favorite thing about this one are all the little white pop-up storms. We didn't know what to call them. First we said thunderheads, and then we realized, well, there's no thunder, there's no lightning associated with these. So we had to come up with something more generic for the time being till we figure out what the reason is for them. And then here's another one where you're really seeing a lot of the different colors inherent in the clouds, but they're stretched now to make them more visible. I really wanted to show in one that wasn't Gerald and Sean, just to show you that there are so many things that people do. They bring different color palettes to the plate. They do different crops, and different people have their own favorites. Our amateur contributors have also been getting a lot of attention from the press, and they're starting now to be interviewed and being featured in different articles. So that's really heartwarming also to see them getting credit for their work. We try to highlight, every week, we highlight one of our amateur contributions on the Mission Juno homepage. And so the Jupiter Blues, Jovian Moon Shadow, and the Stunning Southern Hemisphere are all contributions that we've selected from the actual thousands of pictures that people have uploaded for us. So they're also being showcased here on the main web page. And I'm going to end just with last week's image of the amazing chaos in the northern storms on Jupiter. And it's a dynamesis, either it's a dream or a nightmare, I'm not sure which, but we love it. And with that, I think it's time for Q&A.
All right. With that, now we'll open it up to questions from reporters in the room. Oh, there we go. All right, so now we'll open it up to questions from reporters in the room.
Hi, Ken Chang, New York Times. So one of the things I remember when Juno was just arriving at Jupiter, that one of the big questions was how deep was it, the Great Red Spot? Actually, and I remember Scott saying perhaps it was just a surface feature, perhaps it went down deep. I was wondering, given what you see now, with it going down at least 350 kilometers, what does that say about the mechanism? What does it rule out? What does it rule in for what's generating the storm?
Oh, I guess somebody turned that on. Okay. So I'll start, and then maybe Andy can add to it. I mean, the fundamental question of, how deep are the roots, I think, was a puzzle. A lot of people thought, well, they must be pretty deep because it's lasted so long. Didn't have to be that way. So I think in our data, when we saw that clear indication that there was a warm region that was basically the same size and dimensions and in the same location as the Great Red Spot, just down deep, showed that this storm has got a route that goes at least that deep, 350 kilometers. And while that's pretty new data, there haven't been a lot of models that have now gone in to try to explain that and how it predicts the storm. The fact that it's warmer there is connected to the speed of the winds that you see at the top. And so it has, in fact, in part explained it. There are people that are working on models that basically say, well, the storm, it ought to be just roughly at the depth that we just saw. Now, we looked with the microwave radiometer, and it sees down pretty deep, but it doesn't go to thousands of kilometers. It sees hundreds of kilometers. We see the signature there. We don't see the signature disappear. It just is maintained at the deepest level that we can see. As Andy pointed out, we have other techniques when we fly over it. If we point the antenna at the Earth and get a gravity field measurement, we have to make these basic choices when we fly over. Then we can look another way to see if there's a mass that's even deeper at 1,000 or a couple thousand kilometers, and that would tell us that the route is even deeper. I don't know of any model that would explain that part, but that's possible. So I don't know if I got to your question, but I can let Andy add to the details of what I just said.
I think the data we have rule out a class of models which are kind of close relatives of terrestrial meteorology models. For perhaps practical reasons, a lot of the first efforts to understand the red spot and all the flows on Jupiter borrowed a computer model from Earth science, and we're really telling ourselves, well, you got to stretch your models a little more than that. So it does rule out a class of models. But as Scott says, how deep we have to go to really get it right is still something we're going to work on.
Hi, Jonathan Amos, BBC News. Just to put some numbers on it, the speed of the winds, I don't know how fast the jet stream is on Earth. How fast is the jet stream on Earth? Or how fast are the winds? 40
meters per second, right. Which is sort of over 100 miles an hour.
Okay, so we're 3 times...
you better check me on that, but it's in that ballpark.
Okay, but we're 3 times faster than that in the Great Red Spot.
That's correct. 120 meters per second, and you can work out how many miles per hour that is.
Right, and in your analysis of depth, did I get this right? The edges of the storm are warmer than the core? Is that, did I?
No, at great depth, well, at 350 kilometers, just the opposite. The center is warmer than the edges.
And at the surface, at the cloud tops?
At the surface, no, it's different from that.
Right.
But we've known that it's the red spot is somewhat colder at the surface or above the clouds, but down below it's warmer than the environment, than the same altitudes elsewhere.
And what is it that gives it that distinctive orange tinge?
It's chemical reactions of some sort. I would say it's a little bit like smog. The red spot, we know quite well that the red spot is, the clouds are very high above the red spot, and they're pushed there by the dynamics. But they're very high, and they are trapped there for years, and they cook in the sunlight at these high altitudes, and that turns them red. Now, unfortunately, there are about as many theories as to what chemical reactions are going on as there are scientists who think about it. So we haven't settled that one perfectly yet. But it has to do with the very high clouds in some way. Like that.
You're not sure of some of the chemical species that are contributing to that color?
We know the mix of chemicals, nitrogen. You start with ammonia and methane and water even. But how, and sulfur dioxide, and how you exactly combine them is about as difficult as figuring out smog.
Good, excellent.
Harvey Lyford, freelance, over here. I understand the mission will end next year with one of NASA's famous controlled crashes. Do you expect to learn entirely new things between now and then that you haven't talked about at all? or will it mainly be refinements of what you've already learned?
No, we'll learn new things, but you know, the original mission that we had planned was we were going to fire the rocket again and shorten the orbit to 14 days. And then the mission plan was to do 32 science passes to provide a map around the planet. And using that with 14-day orbits, you would finish sometime next year, as you originally quoted. But last October, when we were getting ready to shorten the orbit, we saw some odd behavior from the plumbing system and made a decision with NASA to stay in the 53-day orbits. What's unique about Juno is the very close passes that Heidi described to you. All of the sciences that we're talking about today is really enabled by these very close passes. And so if you're in a longer orbit, it's pretty much the same. But when you do a map of 32 orbits for 53 days, it takes much longer, obviously. So it goes on for years. And so the plan now is to still finish the missions, and it would go longer than next year. Of course, something could go wrong, or we're going through very high radiation. But I don't think the plan is to shut it off by then. But the real key to your questions are, I think the key answer to your question is that in the remaining orbits, as we complete the map of both the magnetic field, the gravity field, and we get more of all the remote sensing, the polar magnetosphere, we will be discovering a lot of new things. And in fact, a lot of what we've learned and discovered with Jupiter is that our ideas needed to be adjusted, that it was a real paradigm shift. When you got up close to the planet, the deep atmosphere didn't look like we thought, the core and the interior structure didn't look like we thought. We don't actually have the new answers all the time to explain what we've seen. We just know enough to know that we were wrong. And so the rest of the mission really is going to get very critical data in order to help resolve exactly how Jupiter works and how it plays a role in the formation of the solar system and how everything gets put together, you know, in the early formation of the solar system. So all of that is really going to come in the later orbits, as well as a much deeper exploration of the magnetosphere, because one of the advantages of being in a bigger orbit is we get to explore more territory, so we can actually do some science that we originally weren't set out to do.
Okay, great. Hi, Lisa Grossman from Science News. You said that you just happened to go over the Great Red Spot during the one orbit that you've done that. Is it possible to plan for these orbits, or is it?
It was planned.
It was planned. Okay.
Nothing really happens by mistake or
I
accident.
was surprised. All right. So when is the next one, and how often do you expect to do it over the course of the mission?
So we have some flexibility in the planning, because Jupiter is, of course, rotating around in 10 hours, but the winds and the features in the atmosphere are moving relative to its spin, right? And so we can have a little flexibility in changing the orbit slightly to target the red spot. And this is essentially what we did when we flew by the first time. So we have a plan to target the next one late next year, I think it is. Is that right? Candy probably knows that off the top of her head.
Yeah, late next year.
Late next year. And then we see that, I'm not sure I know the month, so I don't know exactly, but it's toward the end of the next year. It's the 17th orbit? Is that what it was? 18th orbit. And then we can see that there are other opportunities, and we're debating on the team now, which ones do we do and why? Because, of course, everything is a choice. You get one science, you give up another, and so how important is it and all of that. But I think that we will probably go over more than once, because we have some outstanding questions, and one of them is, if we can really determine whether this thing goes down thousands of kilometers, even though maybe there isn't a model that explains it, we should go look.
I'd like to point out that we're doing weather forecasting over periods of how many, a couple of years. You couldn't say we're going to pass over Hurricane Flora in 2019. It couldn't be done.
All right, I think we have a question from the chat.
Yes, we have one. We have one from Rick Lovett, who's a freelancer. He wants to know, what is the source of the red spot's interior heat?
The modelers have two things they have to worry about. One is the source of its energy, but that it runs down, if it's going to run down, on a slow, many decadal time period. The other problem is it stable for a week? Because the winds are going around every week. And if it was an unstable structure, it would break up in a couple of weeks. So they've solved that problem, the stability. But the energy, what keeps it going, there's some disagreement about that. I think that, well, we do observe that the red spot periodically swallows little storms, little thunderstorms or big thunderstorms, and it's like a food chain. It's a big fish eating the little fish. And the thunderstorms get their energy from below, because Jupiter's got heat coming out from its insides. So that's my favorite. Studying the red spot and understanding its roots is going to help us answer that question. Maybe a related thing is that it gets energy from the side, and that there's, say, more sunlight at the equator than there is at the pole, and that sort of feeds the energy of the storm. The roots are going to help us with that.
Okay. Do we have questions from reporters in the room?
Jeff Faust of Space News. Just to follow up on an earlier question, how's the health of the Juno spacecraft, and what are the prospects of doing perhaps an extended mission once you complete the primary set of orbits?
The health's excellent. Everything's working really great at the moment, and we haven't seen any signs of degradation due to the radiation, which of course was one of our big risks and big fears. That said, we carefully planned this mission so that the latter half of it was more dangerous than the first half, and we're about a quarter of the way through right now. So this is sort of a status report, if you will, of a quarter of the way through the mission. So we didn't expect to see a lot of degradation yet. But I think we've been monitoring the radiation belts, and while Heidi's certainly seeing things that indicate new populations, in general, I think we're finding that our conservatism was probably the right move, but at the same time, we're also designed correctly to last the full mission. I think there is some hope that we could get an extended mission. But again, it will depend on everything, being in really good working order. And the other thing that you should realize is that the way it's designed is that at the end of the mission, it's getting more and more radiation. And so the last few orbits are the very worst. And if you had an extended mission, they would even be worse than the last few orbits. And so I, of course, hope for as long as possible. But my guess is that if we're able to do an extended mission, it won't be something that goes for 3 more years.
It's a question for Candy, maybe Scott. Do you wish now you had a more capable camera on board? I mean, this Juno cam was added quite late, wasn't it, if I remember rightly? Do you now wish that you had something really quite much better that was incorporated from the word go?
Actually, no.
Yeah.
We're really pretty happy, and at some level, we were forced into a camera design that has turned out to be really nicely suited to this mission. when JunoCam was added, and it was added late, the resources were limited, not just funding, but mass, power, volume, everything you can think of was limited because it had already sort of been divvied up to the other science instruments. So we were forced to decide what's the most important thing, and that will drive the design of the camera. And so we decided, well, the thing that's really unique about this mission is the polar views. And so we designed the camera to give us a great image of the poles of Jupiter. That led to our choice of the wide-angle lens. It's 58 degrees wide, because that was what gave us, from our standoff position of Juno from Jupiter, that allowed us to capture the entire polar region in one image. And then we also knew we wanted color because of the outreach aspect. So, and there's the challenge of putting a camera on a spinning spacecraft. And so that led us to what we call push frame design for the camera, which turned out to work really well for doing things like building up long exposures in the polar regions, which are inherently a bit dark. But the bonus that I myself didn't really appreciate till we started seeing the images coming back is that when we're very close to Jupiter, that wide field of view gives us a context that has really been lacking in previous missions. So in previous missions, well, Voyager, for example, our resolution is about the same as Voyager. And you might say, oh, that's too bad. But the Voyager images were tiny little postage stamps because the narrow angle camera was only about a half a degree field of view, whereas we have that same resolution over a swath that's 58 degrees wide. And so it gives us the opportunity to see that kind of detail in the context of the entire belt or zone or oval, white ovals or whatever.
Maybe I can. If I could add something to that. I agree. I think the camera's just right for what we wanted. And part of it was because we wanted a view that was going to be like we would see if we were on the spacecraft. So if you were really close up to Jupiter and you could look at your eyes, you'd take in a great view. And maybe you've gone on vacations or to beautiful places in national parks or whatever, and you look at a view and you see with your eyes, something incredible. And if you look through a pair of binoculars where you might see higher detail, you get to only look at one spot. You go point to some piece of a mountain or a tree, but you lose the ability to see the context. And that's sort of what, if you had a high resolution narrow angle camera, you're looking through a pair of binoculars and you have to point around everywhere and you never really see the whole context. The other thing is I wanted to kind of correct something, that JunoCam was not added late, actually. It was in the idea from the very beginning. We did have limited resources, Candy's right, and the reason for that was we looked across the scientific objectives that we had to do for Juno, which were mostly focused on the formation of Jupiter, the interior structure, the deep atmosphere, the polar magnetosphere. These were questions that scientists had identified for a long term as very, very important. None of those science objectives really required a camera. We could do it with other instruments. The team and myself couldn't imagine going over the poles of Jupiter and not looking and seeing what they look like. We were all curious. We all wanted that poster in our room. So we looked for a way of getting an affordable camera that would really take the pictures that we wanted and could fit within the resources, because we were going to devote most of the resources to the scientific questions that we were trying to address and get those important questions answered correctly. So that's sort of how the story came to be. I'm not sorry that we have that camera. I think it's a great camera. Would you have benefited if you had an additional second camera that could get super high resolution? Probably. Some spacecraft have been able to have more than one camera on there. But we go over the poles. I'm totally amazed at the images we get. when we get close up to the red spot. So I think that camera just fits. And we had some challenges, like she said, with the spinning, but they were conquered.
That's actually our time. So this will conclude the press conference, but if the panelists have time, they can stick around for more questions. And then we'll reconvene at 4 o'clock for Climate Change Has Unexpected Consequences for Animals. Thanks, guys.